Okay, so let me just write down this the magic formula again, because we'll need it a few more times. So remember, another interesting observation is that if you remember, I derived for you this formula for the Möbius symmetry, and I showed you that we had this formula. So for the Möbius generators, assuming that psi is quasi-primary, we had the formula that Lm with Vn of psi is h minus 1 times m minus n Vm plus n of psi, where psi is quasi-primary of conformal dimension h. But actually, this also fits into this formula. In particular, if you assume that psi is primary, so you call psi primary, so this is quasi-primary. So what this means is that L0 of psi is equal to h times psi, and L1 of psi is equal to 0. Now you call a state psi primary if L0 of psi is equal to h psi, and Ln of psi is equal to 0 for n greater or equal than 1. So the difference is here you only demand it to be annihilated by the one generator of the Möbius group, whereas here you insist on it to be annihilated by all the positive modes of the Virasoro algebra. Now, once you assume that, you see we can calculate this formula using this expression again. So we can calculate what is this. So we can ask what is Lm of Vn of psi. Well, you see we're going to get, so psi here again is 2. So we get the sum from L is equal to a greater or equal than minus 1 of m plus 1, choose m minus L, of V of m plus n LL on psi, right? This is just applying this with a psi being, it's a terrible notation. So what's called phi here is called psi here, and what's called psi here is the Virasoro modes here. So apologize for the unfortunate convention. So again, and now you see again what happens. You see the term with L equals to minus 1 just gives you V m plus n of L minus 1 on psi. Then you have the term with L equal to 0. The term with L equal to 0 just gives you m plus 1 times h times Vm plus n of psi, right? Because the 0 mode of L0 just is h, and then all the positive modes will kill it. So that's the only thing you get. And then remember, this is nothing but minus m plus n minus h minus m plus n plus h Vm plus n of psi plus m plus 1 on h Vm plus n of psi. And therefore, if you combine them, you see the minus h cancels against the plus h. And what this becomes is m h minus 1 into m minus n times Vm plus n on psi. So we learned that the commutator of Lm with Vn of psi has this form, and now this form holds for all m. So this now holds for m in Z, not just m between 0 plus and minus 1, but I had to assume that it's primary. So this formula, you see, this is the quasi-primary formula, and it actually extends to all mode numbers, provided that psi is primary rather than just quasi-primary. Okay, so, but maybe we've now seen enough of that game. Okay, so yes?
So here, we've seen all the examples so far that this is sort of closed among itself. So can you have, so is it always true that like the modes of, say you have phi with phi, the arrow of phi and phi will generate more modes of phi?
Yeah, so in general, you generate also new stuff. But you see, I mean, here, the sum is bounded from below. And eventually, this becomes smaller and smaller in conformal dimension. So it basically tells you the mode numbers of a field of conformal H1 and H2 can involve something of mode numbers H1 plus H2 minus 1 and stuff that's smaller. So here I've indeed looked at example where H1 plus H2 minus 1 closes among the stuff I had. If I go to higher conformal dimensions, I get new stuff, but I always get only finitely many new stuff plus lots of previous stuff. That's sort of the idea. So it's sort of graded in this way, and as a consequence, you can get this under pretty good control. Okay, so this was just there to demonstrate to you that this formula is really useful, and it allows you to understand the structure of, or many aspects of the structure of conformal field theory in quite some detail. Now let's assume that we have a theory. So let's go back to the example with the spin 1 fields, with h equals to 1 fields. So I remember I called them phi a, where a ran from 1 to b, and then I showed that their modes, which I called j, satisfied necessarily the commutation relation. Right? I mean, that's what we just showed on in the other blackboard. Now, you see, this theory, to start with, you would think is not conformal, because I've just written down the modes of the affine Kac-Moody algebra. So the question is, can I construct a stress energy tensor out of this theory? So, or put it differently, is this theory conformal? Well, so you can try to find the conformal vector. So what I mean by the conformal vector, I want to find the vector whose modes are just the Virasoro modes. So the question is, what is this? Well, so we know because of this formula up there. You see, if we write this formula for the L's, then we would, the Vn of psi we would write as JAN. This has h equals to 1, so the first term isn't there. So this will just go like minus n times JAM plus n. So in particular, you see that the zero modes of JA commute with Lm. Because if n is 0, then the right-hand side is always 0. So this should mean that this state should be invariant under the global Lie algebra. And therefore, a natural ansatz for this vector is, so let's assume that I can diagonalize it. So let's assume that I can write it like that. So it's some simple Lie algebra. I write it as, I choose some orthonormal basis. So these guys are totally antisymmetric, and this guy is just proportional to the identity matrix. So then a natural ansatz for phi is that it's of the form lambda times JB minus 1, JB minus 1, acting on the vacuum, where the repeated B means I sum over all the B's. So this is my ansatz. And we have to fix the parameter lambda. Well, we have to check whether it works. And in the process of checking that it works, we'll fix the parameter lambda. And in the process of fixing the parameter lambda, we'll calculate the central charge of the associated Virasoro algebra. Okay, let's see how this goes. Well, the first reason why this is plausible is that this is going to be a singlet with respect to the global Lie algebra. So why is this? Well, I would expect that the zero mode should be equal to 0. It should transform as a singlet under the action of the zero modes. So what is this? Well, I mean, the zero modes kill the vacuum, so I can calculate it. So this is the commutator of JA0 with JB minus 1, JB minus 1, plus JB minus 1, the commutator of JA0 with JB minus 1, all acting on the vacuum. Now, what is this? Well, we know what this is, right? This is I times FABC JC of minus 1. There's no central term because it's a 0 and a minus 1. They don't add up to 0. So this is equal to I times lambda times FABD times JD minus 1, JB minus 1, plus JB minus 1, JD minus 1 on the vacuum. Okay, so what can we say about that? Well, that's obviously 0, right? Because you see, this is symmetric under the exchange of B and D, whereas the structure constant is totally antisymmetric in the three indices. So therefore, this is equal to 0 by the antisymmetry of the structure constant. So, I mean, the structure constants are manifestly antisymmetric in A and B, but for a simple Lie algebra, I can choose them that they are totally antisymmetric in A, B, and C. And it doesn't matter whether the C is written downstairs or upstairs, because the metric with which I raise and lower indices is just the delta matrix. So it doesn't matter in this basis. Okay, so this is a reasonable candidate because it's annihilated by the zero modes. What about the plus 2 modes? What can I say about the plus 2 modes of this? Okay, well, I can similarly calculate. So this is going to give me lambda, and then I'm going to get the commutator of JA2 with JB minus 1, JB minus 1, plus the commutator of JA2 with JB minus 1, all acting on the vacuum. Okay, so the JA2 JB minus 1 will give me I times FABD JD plus 1. So this I can write as lambda times I times FABD. And then I'm going to have a JD plus 1, JB minus 1, plus JB minus 1, JD plus 1, acting on the vacuum. Okay, now that term is clearly 0 because the one mode kills the vacuum, so this dies. And here I can replace it by the commutator, but the only term that from the commutator will survive is the central term because the vacuum is annihilated by the zero modes. So the only term that will survive is proportional to delta BD, but again, because of the total antisymmetry of the structure constant, that is going to be equal to 0. Okay. Okay, so now I've put in the JA0, JA2, so what about JA1? And I mean, you may ask, why do I calculate them? You see, what I'm going to do is I'm going to apply the mode expansion for J with L. And for that, I need to know the action of the positive J modes on the state phi L. And I'm just calculating them, and then I'm plugging them into this formula. So I need, the last one I need is the one mode. Now, the one mode is the fun mode. Not always, but in this case. Okay, so I have to calculate JA1 on phi. So this is lambda times JA1 on JB minus 1 on JB minus 1 plus JB minus 1 on JA1 on JB minus 1 on. Okay, so now there are two terms, right? There's a term that goes like, so this term can be equal to K times delta AB. And obviously this term can be equal to K times delta AB. So I'm going to get a term that looks like the lambda times 2 times K times, and what's left behind will be a J A minus 1. Right? There will be a term that will go like JA minus 1 on the vacuum. This is what survives from here. So I get a K from here, and I get a K from here. In addition, I get a term that looks like plus I FABD JD0. Now here it acts on JB minus 1 on the vacuum, whereas here it will act directly on the vacuum. So when this guy acts on the vacuum, this is 0, because the vacuum is annihilated by the 0 modes of J. It's only the minus 1 modes that do something. Whereas here, it's not doing this well. Whereas here, you see, this is going to be equal to the commutator of JD0 with JB minus 1. So this will be equal to I times FDBC JC minus 1 on the vacuum. So what we are going to get is a term that will look like lambda times 2 times k times JA minus 1 on the vacuum. This is the guy that comes from here and from here. And then we get a term that looks like minus. And then if we rewrite this, we can write this as BDA. Let's write all the indices upstairs. BDC JC minus 1 on the vacuum. Right, so what I've done here, so the I times I gives me a minus sign, but here I flipped the order of D and B. So I flipped these around, so they've become BDC, and these I've cyclically permuted, so they are BDA. So this is a combination of structure constants. So you have a structure constant FAB, you have FBDA times FBDC summed over B and D. And now it's a fact of simple Lie algebras that this is equal to the quadratic Casimir in the, this is basically the quadratic Casimir in the adjoint representation times delta AC. So what you learn from that is that this is equal to lambda times 2k plus q times JA minus 1 on the vacuum. So this is a fact about Lie algebra. I mean, if you think about it, this is basically the quadratic Casimir. The quadratic Casimir is JA, and if you act in the adjoint representation, it acts by commutator. So it gives you an F, and then it gives you another F. And if you go through, this is the value of the quadratic Casimir in the adjoint representation, and that's conventionally called Q. Okay, so now we have collected together all of these things. So now we simply work out the commutator of the J modes with the L modes. You see, now we can calculate this. Well, sorry, not with the L modes, with the modes of phi, right? So what this tells you is that JAM with Vn of phi, where this phi is this phi, right? Is this phi. Maybe I should call it phi L. So it's a specific phi. I should have written everywhere, I should have written phi L, right? This is the specific ansatz for this state. Okay, so what is this commutator? Well, remember we're going to get a sum from L equal to 0 to, so we have an L equal to 0 term. The L equal to 0 term is always just this. So this gives me Vm plus n of the 0 mode. But you see the 0 mode was 0. This is, you can see this, right? This is this equation. So the 0 mode is 0. The 2 mode is 0. The 3 mode and higher will be 0 because then you had negative conformal dimension. So the only term that survives is actually the 1 mode. So we only have to keep track of the 1 mode. So if L is equal to 1, then this is m choose m minus 1. So this is therefore equal to m. And then what I'm going to get here is, well, what do I get? The 1 mode gives me this prefactor. So it's m times lambda times 2k plus q times the mode, the A mode, JAM plus n. Right? That's what we've calculated based on this ansatz. But now you see, if you choose lambda, so now choose lambda to be 1 over 2k plus q, then what you observe is that Vn of phi L, let's write it, Vn phi L of JAM is equal to minus m times JAM plus n. So therefore, you see, that has exactly the form that it was. So that looks like the Ln modes, because the Ln modes with JAM should just give you minus the mode number of J, which unfortunately I've called M here. So I should have really called that M and that N. Then this would have been an N, right? Then this would have been Ln. So the modes of this funny state for that specific choice of the normalization convention gives me exactly the correct commutation relation that I would have expected from the Virasoro algebra. So that makes me believe that probably phi L is the state, phi L with lambda being this value, is the state that describes the stress energy tensor, because its mode do the right thing on the fields of J. And that comes again out of this magic formula, right? It's just a direct consequence of the structure of it, plus, I mean, I knew that the J with J commutator was hardwired. I made this ansatz, and everything else I could just deduce. I didn't make any further assumptions. Okay, so, but what that should mean is that the modes of this guy with itself should form a Virasoro algebra, and in particular, I would like to determine the central charge of this Virasoro algebra. So what's the central charge of this Virasoro algebra? If it is a Virasoro algebra. Okay, so let's check what it is. Okay, so now we want to calculate the modes of L with L. So let's call Lg of Z the field V of phi L of Z, where phi L is defined by this ansatz with this normalization factor. And now we want to calculate Lg of Z, Lg of zeta. And then we know that there will be a fourth order pole, which will be L2 of G on phi L of zeta. I'm now writing it in terms of the operator product expansion. I could write it in terms of commutators, but it's the same thing. Then I would have plus V of L1 of G on phi L zeta Z to the minus zeta cubed plus V of L0 of G on phi L zeta Z minus zeta squared plus, and then the L minus 1 term is a d by d zeta. So this I can just write as Lg d by d zeta of Lg of zeta Z minus zeta. So what I have to check in order to see that it's a Virasoro algebra, I have to check that this is equal to 2. I have to check that this is equal to 0, and then I have to evaluate this, and this should give me the central charge, right? That's the structure of this OPE for the Virasoro algebra. So you see, this is easy to see because you see phi L is made from two J's, and I know the commutators of the modes of phi L with the modes, so therefore you can see that the zero mode of this with this is just minus the mode number, so this comes out automatically, right? Do you see this? So L0 of G on phi L, what is this? Well, this is V0 of phi L on JA on lambda times JB minus 1, JB minus 1 on the vacuum. But I know what the commutator of this guy with this guy is, and the commutator of this guy with this guy by virtue of this formula. That's the formula I honestly derived. So I know that they just they increase the conformal dimension by 1. This increases the conformal dimension by 1. So this has conformal dimension 2. So this is, comes out correct. And likewise, you see, if I apply the 1 mode to it, this will be the 1 mode. And then I'm just going to get the same calculation as I had before, because you see, this is just going to, so what is this going to give me? This is just going to give me lambda times the commutator of phi 1, phi L with JB minus 1 on the vacuum plus JB minus 1 on the vacuum of V1 of phi L with JB minus 1 on the vacuum. But this I've just calculated. The one mode of this with Jn is just minus n Jn plus 1. So this is just JB0, right? And this is just JB0. JB0 kills the vacuum, and the commutator of JB0 with JB minus 1 is 0, and therefore it also kills the vacuum. So it's manifestly this is equal to 0, so therefore this term isn't there. Right? So it simply comes, I mean, once you've derived that this works, you can work out what these OPEs are using recursively this knowledge, given the fact that you know how the modes of this act on J, and therefore you know how it acts on the state phi L, because phi L is made out of two J's. Since you know what it does on the J's, you can deduce what it does on the phi L's. In particular, we can calculate what it does, what the 2 mode does, the central term. So what is the central term? Okay, let's maybe go to this blackboard. So what we want to work out is phi L, phi V2 of phi L on phi L. So this is V2 of phi L on lambda times JB minus 1 on the vacuum. And we just use this commutator. So this is lambda times V2 of phi L JB minus 1 plus JB minus 1, the commutator of V2 of phi L with JB minus 1 acting on the vacuum. And now we know what this is. By this formula, this is just JB plus 1. This is just JB plus 1. So this term dies because J plus 1 on the vacuum is 0. And what is this? JB on 1 on JB on minus 1. Well, that's the central term of the Virasoro of the Kac-Moody algebra. So this gives you lambda times k times the dimension of G. Right? Because you get for each B, you get a factor. Remember, the commutation relations are JAM, JBN is I times FABC, JCM plus N, plus M times K times delta AB, delta M minus N. So this commutator, this term is 0 because you have the same label twice. The only term that survives is this guy. You get a factor of 1 times K, but B is to be summed over. So you get as many terms as there are basis elements in your Lie algebra. So this term is K times dimension of G. So this is equal to C over 2. Because that's the coefficient that determines the central term of the Virasoro algebra, because the fourth order pole is C over 2. So therefore, you deduce that the central charge of this Virasoro algebra so the upshot of this is that phi L, which is equal to 1 over 2k plus q times JB minus 1 on the vacuum, generates a Virasoro algebra with central charge C is equal to K times the dimension of G. Actually, it's 2K, right? Because if you bring the factor of 2 to the other side, it's 2K times the dimension of G divided by 2K plus Q, which you can write as K times the dimension of G divided by K plus Q over 2. And Q over 2 is often called the dual Coxeter number. So here HV is Q over 2. And for example, if you take G to be SUN, then HV is going to be equal to N. So for example, for SUN level K, that will give you a central charge of the form K times N squared minus 1 divided by K plus N. And in particular, you see now that this central charge is generically not an integer or half integer, so this is not a free conformal field theory anymore. If it was a free conformal field theory, if you could write it in terms of free fields, then the central charge would have to be a half integer or an integer. But this is some rational number, and generically, this is not a free conformal field theory. But what you've shown is that if you just start with some set of spin 1 fields, this structure sort of comes out automatically. Yes?
So last week we have seen the Katsuni algebra for fermionic fields, on half fields, and now we have seen it for H equals 1 field.
So there were also H equals to 1 fields. So last time, so what we did last, it's a good question. So last time, we actually gave a free field construction for this, for the case when K is equal to the dual Coxeter number. So the free field theory from last time, for the free fermion from last time, realizes this for K is equal to the dual Coxeter number. Because you see, then you have the dual Coxeter number divided by the dual Coxeter number plus the dual Coxeter number. So this gives you a half, so you get a half times dimension G, and you had exactly dimension G free fermions, each of which have central charge a half. So the free fermions actually realize the affine Kac-Moody algebra with the level being equal to the dual Coxeter number. So if you take 3 of them, you get SU2 at level 2. If you take 8 of them, you get SU3 at level 3. If you take 15 of them, you get SU4 at level 4, and so on. So, but also there, the fields were spin 1 fields. Remember, the currents that we wrote down were of the form JA was of the form FABC, psi B, psi C, right? Psi B and psi C each have conformal dimension a half, so they're always spin 1. So the Kac-Moody generators are always spin 1. But what's the value of K depends on what you do. So there we picked some free fermions. Then we get this construction at a specific value of K, and now I can tell you that's the value of K you would get it at. But here I've taken the point of view, I'm not assuming I know how I get the currents. I just assume somebody gives me a conformal field theory with some spin 1 currents. Then I showed you first that necessarily the spin 1 currents generate an affine Kac-Moody algebra. And what I've just demonstrated to you is that they also automatically generate for you a Virasoro algebra with a specific value of the central charge, and the value of the central charge is this value.
So would a general strategy to analyze a 2D field for any spin field to be to construct some current which is spin 1 and then look for Kac-Moody theory?
Absolutely. So if somebody hands you a conformal field theory, the first thing you should look at is does it contain any spin 1 fields? Because the spin 1 fields, you basically know the structure. The spin 1 fields will generate you an affine Kac-Moody algebra, and it will generate a Virasoro algebra with that value of the central charge. But that may not be all of it, and that's what I'm about to explain next. So the strategy is sort of the deconstruction strategy. You try to first look at the spin 1 fields. You know the structure of the spin 1 fields. And what I'm going to explain to you in the next step is how you can effectively remove the spin 1 fields and ask what is the rest. So let me explain to you what the rest is. And then, but unfortunately, so spin 1 fields, there's a clean answer that I've given you. Unfortunately, that's where it stops having a clean answer. So for the spin 2 fields, And that's, I think, a question somebody asked. You see, in the OP of two spin 2 fields, you generate generically a spin 3 field. And in the OP of two spin 3 fields, you generate a spin 5, 4, 3, 2, 1, 0 field, and so on. So it's only for one fields that you close among themselves. If you go higher, you generate more complicated stuff. But if you can recognize a piece of it, then you should always take advantage of the piece that you recognize and then remove it from the rest. So in which sense can you remove it from the... So by the way, this is called the Sugawara construction. And I mean, it's actually, so I think it's taken, I think, about 10 years or so to get the Sugawara construction straight from the first attempt in the literature. So this factor, the plus Q correction term here, is something which people missed at first. And so in this way of describing it, it sort of comes out, but this is with hindsight. I mean, when first people wrote down, they didn't spot this and so on, but that is the correct description, and that is the correct value of the central charge, and that plays a very important role, as I'm about to explain. Okay, suppose now we do exactly as you asked. Suppose you give me some conformal field theory, and I'm looking at the spin 1 fields. So suppose we have some CFT. So suppose we have some CFT. And it contains some spin 1 fields. Let's call them JA. And as I just explained to you, they give rise to a Virasoro algebra, which I called LG, via the Sugawara construction. And this has central charge C equal to Cg, being equal to K times the dimension of G, divided by K plus the dual Coxeter number. But suppose the CFT you were given also had a stress energy tensor L. A priori, you don't know whether the stress energy tensor of the full conformal field theory agrees with the energy momentum tensor you calculate out of the bilinears of the currents. So what can we say generically? Well, suppose we define the modes Km to be the modes of the Virasoro modes of the CFT as it was given to you, and we subtract from them the Virasoro modes that I construct via the Sugawara construction. What can I say about these modes? Well, you know, differences of modes typically don't satisfy good algebras. I mean, if you have some modes that satisfy a good algebra and you have another set of modes, then the sum typically leads to happiness. The difference typically leads to unhappiness, because you see, the commutator of two minus signs gives you a plus sign. So you're not going to land on anything that's manifestly has any chance to be anything nice. But let's think about what we can say about this guy. Well, remember, we know on general grounds that for the stress energy tensor, we have that the modes of the stress energy tensor must have this form with respect to the currents. That's if there are spin 1 fields, then we know the full stress energy tensor of our conformal field theory will satisfy this commutation relation with the currents. But the way we constructed this Sugawara expression was that these modes also have this property. I mean, that's exactly how I just constructed it for you. So we also know that the modes of the bilinears of the currents that make up the Sugawara construction also have the correct commutator with the currents. So therefore, you see the difference of Lm minus Lgm must commute with the currents, because L has the same commutation with the currents, Lg has the same commutation with the currents, so the difference commutes with the currents. So we conclude that the difference commutes with the currents. But if the difference commutes with the currents, it must also commute with everything that you make out of the currents. And therefore, it must commute with Lg, because Lg is bilinear in the currents. So therefore, it also follows that Km with LGN must be equal to 0, because this thing is basically made out of the currents. And if K commutes with the currents, it commutes with the bilinears of the currents. But now we are in business, because you see, now we can actually calculate what this commutator is. So what is this commutator? Well, now it's very simple, right? So now we just write down what's the commutator of Km with Kn. Well, we say this is the commutator of Km with L m minus Lmg. Sorry, Ln minus Lng. But we've just seen that this term is equal to 0 because K commutes with the LGN. So this is the commutator of Km with Ln. But now I can write Ln. I can also write Ln or Lm as Km plus Lgm. No, I think I'm making a mess of myself just now. That's not what I want to do. Okay, maybe I don't want to do it that way. Let me do it some other way. So let's use this formula to write it as Lm is equal to Km plus Lgm. So we know that the Lm's, they satisfy m minus n times Lm plus n plus c over 12 m into m squared minus 1 delta m minus n. But I know that this is also equal to Km plus Lgm, Kn plus Lgn. And therefore, because the K's and the Lg's commute with one another, this is of the form Km with Kn plus Lgm with Lgn. Because the cross terms vanish because the K's commute with the Lg's. Okay, so I don't know what that is. That's what I'm about to find out. So this is Km, Km, Kn. But I know what this is because this is the Virasoro algebra that I've just constructed for you. So this is m minus n times Lg of m plus n plus Cg divided by 12 times m squared minus 1 delta m minus n. Okay, but now you see we have a formula because you see Lm with Ln was equal to that, but it's also equal to that. So now we can solve for the commutators of Km with Kn. So what do we get? Km with Kn. Well, it is m minus n times Lm plus n minus Lg m plus n. But Lm minus Lg is just K m plus n. Right? I bring this to the other side. So then this becomes this guy minus this guy, which is exactly this guy. Plus the central term is just C minus Cg over 12 times m into m squared minus 1 delta m minus n. So the miracle is that the difference of the two stress energy tensors satisfies yet another Virasoro algebra. And the Virasoro algebra it satisfies is the one whose central charge is the difference between the central charge of the full conformal field theory and the central charge that I can make out of the Sugawara construction out of the bilinears of the currents. So this basically decouples your theory into the bit that comes from the currents plus the rest. And the rest has its own Virasoro symmetry, and the Virasoro symmetry of the rest is the stress energy tensor generated by the currents of the Km's, whose central charge is simply the difference between the central charge of the full thing minus the central charge of what the bilinears of the currents give you. So that's what's called the coset construction. or GKO construction. So it achieves exactly what you were hinting at. If somebody gives you a theory, you look at the spin 1 fields, you understand the structure of the spin 1 fields, and then you can sort of remove it, and the rest will be a bona fide CFT by itself, but it will be a CFT whose central charge is reduced by the central charge of the piece that comes from the currents. And so in particular, if the central charge is equal to the central charge of ZG, then there is nothing left. Then basically the currents generate everything, but if there's something left, if the central charge you should think of as being counting degrees of freedom, so if there are degrees of freedom left, then this piece will be non-zero and it will generate the remaining bit. And then you can look at the remaining bit and analyze it in turn. Yes?
So can I remove, instead of removing all the spin 1 fields, can I remove the subalgebra?
Absolutely. So the original construction of the coset construction was that you did this for two Sugawara expressions. So you had a numerator algebra and a so the original coset, I mean the reason why it's called coset construction actually maybe it's instructive to write this down because I'll maybe come to that in a second. So in particular you can do what he suggests. You can start with a theory that's generated by the currents in some G level K algebra, and then look at the subalgebra of some currents that live in some H K prime. So the standard example is, suppose you take SU2 level 1 plus SU2 level K. So suppose your theory that you start with has 6 currents, 3 of them generate an SU2 level K algebra, and 3 of them generate an SU2 level 1 algebra. Then this contains a subalgebra which is SU2 level K plus 1. Right? So if you call, say if you call these J's, and these you call K's, then the generators of these will simply be JA plus KA. And if you think about the form of the affine-Kac-Moody algebra, then central terms will simply add. Is this clear? So you could, for example, play the game in this setup. You could say the big theory I start with is also generated by currents. It's just generated by more currents. And then I'm looking at the sub-theory that's just generated by the diagonal pieces. So what is the central charge which I'm going to get for the coset? So then the coset will have central charge. Well, it will have central charge of this guy plus this guy. So what is this? So remember the central charge of SU2 level K is K times the dimension of G, which is 3. So it's 3K divided by K plus 2, because the dual Coxeter number of SU2 is 2. So what is the coset algebra? Well, so you have 3 for K equals to 1. This is 3 divided by 3, so this is 1. Plus, then you have 3K divided by K plus 2. And then you have to subtract 3K plus 1 divided by K plus 3. Right? I mean, so this is the central charge of SU2 level K. This is the central charge of SU2 level 1. And this is the central charge of SU2 level K plus 1. So which central charge do you get? Well, okay, so now I'm going to make a fool of myself, but let's try. Okay, so obviously we want to bring this onto a common denominator, so we want to have K plus 2 times K plus 3. And now we have to multiply this out. So we get 3K into K plus 3 minus 3K plus 1 into K plus 2. Right? This is the central charge as I have to calculate it. So let's hope for the best. So what is this? So this is 1 plus, so let's work out the numerator, 3K squared plus 9K minus 3K squared. So how many minus 9K? right? So there is 2k plus 1k is 3k plus 3 is 9k minus 6 divided by k plus 2 times k plus 3. And lo and behold, you can write this as 1 minus 6 over m into m plus 1, where m is k plus 2, and m plus 1 is therefore k plus 3, right? Because this cancels against this cancels against this, and you keep the minus 6 over m into m plus 1. Now, okay, this looks like another random formula, but this is a magic formula, which you may have seen. These are the central charges of the Virasoro minimal, the unitary Virasoro minimal models. So, for example, for m is equal to 3, this becomes 1 minus 6 over 12, which is 1 minus a half, which is a half. For m equals to 4, it becomes, so this is the Ising model. Then for m equals to 4, it's the tricritical Ising model, and so on. So these are the central charges of very special conformal field theories that I'll come to in the next, in the next lecture, I'll try to, I'll also mention to you this formula. I'll try to get to you why these are the special conformal field theories and why they're important. What this is suggesting to you is that you can engineer them out of the coset construction by just starting with affine theories, with theories made out of currents. And this is in fact the general belief that many or most or all conformal field theories you can construct by an analog of that sort of way. You look at currents, then you look at the coset construction, you look at orbifolds of the coset construction, blah, 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 but grosso modo, people believe that will generate essentially all there is under the sun. I'm not 100% sure I really agree with that sentiment, but that's what many people believe, but I don't. So what I mean by that is the modes satisfy the algebra where these are the structure constants of SU2, and this parameter k I call the level. So it generates an affine Kac-Moody algebra where k, this magic number, takes the value 1 or... And k, actually that's another thing I'm going to explain to you in the next lecture, is k wants to be an integer. The world is much, much happier if k is an integer than if it's not an integer, and you'll see in the next lecture why that is so. What's so special about the integer level current theories, and this tells you that this tells you that somehow there are Virasoro theories with this value of the central charge that should somehow be special, and we'll see how they arise. Yes?
So we have seen that it's been one field always form a sub-Virasoro algebra of the entire thing. Does it sometimes happen that other fields also form a sub-algebra?
Well, there's one other example which are the spinor half fields. The fermions you can equally also always remove. But it's the spinor half fields and the spin 1 fields that sort of form things by themselves. But as I was trying to explain, you see, if you look at the structure of this mode algebra, so I mean, I'm only going to sketch it, but suppose you look at the commutators of two such modes. Then we had the form L is equal to minus h psi plus 1. Then there was some numerical coefficient. And then we had the L mode of psi acting on phi, right? So now you can ask, so what are the conformal, so suppose this has conformal dimension h1, and this has conformal dimension h2, what fields will appear here? Right? And what's the leading term here is, okay, so this has conformal dimension h2 minus L, right? But L can be greater or equal than minus h psi. So minus L will be less or equal than h psi minus 1. So this will therefore always be less or equal than h1 plus h2 minus 1. So generically, in the OPE of a field of spin conformal dimension h1 and h2, you'll discover fields up to conformal dimension h1 plus h2 minus 1. So if you start with 1, 1 plus 1 minus 1 is 1. That's the magic. 2 plus 2 minus 1 is 3. So you start with 2 spin 2 fields. Generically, you produce a spin 3 field. 3 plus 3 minus 1 is 5. So you start with 2 spin 3 fields, you generate. So it gets worse and worse and worse. So the things you can sort of decouple is the stuff that closes among itself. So if it's a half plus a half minus 1 is 0. So the fermions can't produce anything. 1 plus 1 minus 1 is 1. But from there onwards, generically, you produce stuff that doesn't close among itself. So that's the reason why you can only generically remove the spin a half field and the spin 1 fields, and higher up, the world is complicated.
That one needs has to go case by case.
Well, I mean, you see, generically for a half and 1, it always works. In the higher case, okay, the Virasoro algebra always closes among itself, but there are algebras generated by spin 2 fields that don't close among themselves. So, for example, the monster theory has 196,883 fields of conformal dimension 2, and they form an algebra that produces all these fields at spin 2, but also some spin 3 fields. And the spin 3 fields are forgotten. They are the next term in the J function, right? I mean, so it's the next irreducible representation of the monster group. So it's a few million fields. So, okay, there are simple algebras. There are W algebras where you get closed form algebras, but the W algebras you get mostly by the coset construction. So they are the most efficient description for the W algebras in terms of cosets of currents. So, yeah, so I think, the problem is that it's the lamppost problem, right? So now you think you have everything under control, but that's because you know so little. Once you explore more, and I think our idea that everything is simple is probably not true, but there are interesting theories we can get under control by these sort of techniques. There are theories which we can't get under control by these techniques, but we also can't get under control by any other techniques. They're just more complicated. There's Liouville theory, there is SL2R, all this stuff which sort of the more modern developments go into. But this is sort of the classical description, the neat, rational, conformal field theories that you can get under control, and they you can describe in that fashion. And I'll explain, again, I take the currents, I explain to you how you can understand the representation theory of the currents, and I explain to you how you can understand the representation theory of the minimal models.
But are there CFTs known with non-rational central charge?
Sure, Liouville.
Yeah, but does it then mean that there are CFTs which cannot be constructed by the coset construction?
Well, okay, but then you sort of tweak it a little bit. Okay, so maybe the rational CFTs can be constructed, but I don't even believe that all the rational CFTs can be constructed by the coset construction. I think the world out there is richer. There are logarithmic CFT. I could give you a whole lecture on logarithmic CFT, but you probably don't want to know. But it's another rich corner that doesn't fit into people's ideology about. People know simple construction, and they somehow believe everything is a simple construction then. I don't believe that's true. On the other hand, I think there's enormous merit in these simple constructions because there are interesting theories you can analyze that way. So that's what I'm trying to teach you, how to analyze interesting theories that way, but you shouldn't go away believing that you've conquered conformal field theory for good. So I want to strike that balance. I don't want to discourage you, but I also don't want to make you overconfident. Any other questions, or shall we take a well-deserved break and then continue? Okay, so so what you're doing here is basically studying simple examples of conformal field theories that we have under control, but some of the things I wrote down are also true in general. So this OPE relation is true in general, but it has a simple, manageable form for the currents. And what I'm trying to say is that these are sort of the paradigm examples where you see how this works, and they generate interesting classes of examples, but then there are obviously more complicated examples out there that may be more tricky. Now, what I next want to explain, so what we are aiming to is understanding the representation. So far we've only looked at the chiral fields, But before I get to the representations, I want to also make a comment about the correlation functions. So here I've studied the OPEs. So suppose we look at the spin 1 currents. I should probably take this off, otherwise this will... But now I have a problem. No, I manage. I think I manage. No, I don't. This is non-trivial winding.
Yes, you unwind it.
Now I've unwound. So let's suppose we have some spin 1 currents. So there's some, I mean, the reason I'm telling you, so basically I'm just trying to tell you neat stuff. So what are neat observations you can do? So remember, for the spin 1 currents, we said that the modes satisfy necessarily the affine Kac-Moody algebra. And this is just the mode expansion version of what we would write if we wrote down the OPEs. And in terms of OPEs, this looks like JA of Z, JB of zeta. This is the term that has a double pole. So this will go like K over 2 delta AB divided by Z minus zeta squared. And this is the simple pole plus FABC JC of zeta Z minus zeta plus regular. I mean, you can go between the two things either way. I mean, for example, one way of getting this is to remember that this term should be V of JA1 on JB minus 1 on the vacuum at zeta divided by Z minus zeta squared. And this term will be JA0 JB minus 1 on the vacuum of zeta Z minus zeta, and then you just apply the commutation relations, right? I mean, you can go from the commutators to the OPEs, and you can go from the OPEs to the commutators. They contain exactly the same information. So, I mean, here you know that this is probably then K delta AB, because you get I mean, this is just this term that survives, right? The only term, the zero modes kill the vacuum, so the only term that survives the central term, so it goes like K delta AB. And then this term, only this term survives because there is no central term. And this will just give you this with this coefficient. So these are sort of equivalent ways of writing it. Now you can ask, suppose I know the OPEs of these currents, what can I say about the correlation functions? So I could ask, what can I say about this sort of correlation function? An L-point function of the currents. Now there's one simple recursive way in which you can calculate correlation function that you can always do. So that's another useful general lesson. So the idea is, okay, so this is a function of Z1 up to ZL, but I can think of it as a function of Z1 when I fix Z2 up to ZL. So if I think of it as a function of Z1, this formula there tells me where the poles are. The poles are when Z1 gets close to any of the other Zs, there's a double pole, potential double pole, and there's a simple pole. So what are the poles of these functions as a function of Z1? Well, as a function of Z1, it's the sum over, okay, let's call this n, because it wants to be an n-point function. So it's going to be a sum from L equals to 2 to n. And then I have the term I times F A1 AL C over Z1 minus ZL times the correlation function where I have A2 of Z2 up to ZAN up to Zn. And in the place of the Lth guy, I now write ZJC of ZL plus the sum from L is equals to 2 to n, K times delta A1 AL divided by Z1 minus ZL squared times the correlator JA2 up to JAL, except JAN, except the Lth term is missing, right? I mean, basically what I do is, so the j, the 2 to n are fixed, and I'm the guy sitting at z1, and I'm walking around the complex plane and see what happens. As I walk around the complex plane, nothing happens, no pole. But whenever I get close to any of the other j's, I have a simple pole. The simple pole will have this form, and then the rest of the points are far away. So at the point where the simple pole is, I have to replace JA, JB by FABC, JC. And then it can also happen that I have a double pole, and then just this field disappears. So these are the poles of this function as regarded as a function of Z1. And I've reduced this endpoint function into an n-1 point function, because you see, the first one has gone, and the th one has replaced by another field. So I've lost one j, and here I've lost two j's. So this is a recursive formula, right? It replaces an endpoint function in terms of an n-1 point function and n-2 point function. But I haven't yet shown it's identical. This is just the poles of this function as a function of Z1. So the statement is, if I think of this function as a function of Z1 for fixed Z2 up to Zn, then its poles are all of that form. Okay, so therefore, if I subtract the poles from this function, then the difference doesn't have any poles anywhere in the complex plane. So as a function of Z1, the difference is an entire function. It's an analytic function. But then, you know Liouville's theorem. You know how this field has to behave at infinity, because at infinity you can use the mode expansion and you see how it behaves at infinity. It must be bounded, and it doesn't have any poles. So by Liouville's theorem, the difference must be equal to 0. So therefore, this is indeed an identity. So this allows you to write an endpoint function in terms of an n-1 point function and an n-2 point function. So this is an endpoint function, right? But this has only n-1 fields, and this has n-2 fields, right? Because the 1 and the L are missing, and here the 1 is missing, and the L has been replaced by another field. So therefore, this gives me a machine to calculate it recursively, all of these correlation functions. It's a little bit of work, because I have to do it many, many times. But in principle, it's clear how to do it. In fact, you can do even better. So I said, in principle, it's hard to do it, but actually it's not. You can write down a closed formula that gives you the entire answer. So what's the closed formula? Well, the closed formula looks a little like Feynman diagrams, but it's not really Feynman diagrams. So the idea is that let's look at all permutations. So let rho be a permutation of Sn without fixed points. So rho is a permutation, so it's a map that maps the points 1 to n to the points 1 to n, and no fixed point means there is no j that gets mapped to itself. Everybody is mapped to somebody else. So any such rho I can write as a product of cycles. You know, any permutation you can write in this cycle shape. Right, so how do you do this? So you say, suppose you do this explicitly, you say, okay, where does 1 go to? Okay, 1 goes to 7, and then 7 goes to whatever, and then 7 goes to 5, and then 5 goes to 1, then you close the bracket, and then you take the next number that you haven't got, and you can just write any permutation in terms of cycles. So what I'm going to claim is that you can write the correlator. So we are going to sum over all permutations that do not have a fixed point. So not having a fixed point means none of these cycles has length 1. If it was a cycle of length 1, that would be a fixed point, because that number would just go to itself. So this will have, rho will consist of cycles, and each cycle has length bigger or equal than 2. So now let sigma be one of these cycles. So to each cycle, we associate the following function. We associate the function trace of k of t. So let's assume the points in sigma are, so let's assume sigma is of the form I1 up to IP. where I1 and up to IPs are numbers from 1 to n. So then we are going to take the currents Ti1 up to TAIP. So to each such cycle, we associate the following function. We take the trace, and then we take the product. So we divide this by z of I1 minus z of I2 times z of I2 minus z of I3 up to z of I3 at P minus P minus z of I1. Right? So, okay, so let rho be a permutation of Sn. Let's write rho as a product of cycle. And for each cycle, we associate this function, where k is an operator that commutes with the t's, and trace is just some trace, so it's cyclically symmetric in the t's. So this is some number, and then we divide it by the products of differences of z of the first point with z the first point of minus z the second point times the second point minus z the third point minus z the fourth point, and so on. And then the claim is that this, the current, is the sum over all such permutations without fixed point. And then, so let's call this function f sigma. And then it's the product over the sigma in rho, over the cycles in rho, f sigma. And I claim that that's the correlator. So the correlator of these currents I can write as a sum over permutations without fixed points. For each cycle I assign this function. Then I take the products of all the functions associated to all the cycles, and then I sum over all the permutations without fixed point, and I claim that's the answer that you get by doing this game recursively. Now, why is this true? Well, think about it. I mean, what you have to show is that this function reproduces correct all the OPEs. I mean, the only thing you have to show is that this answer reproduces all the correct OPEs. Okay, so let's check whether it reproduces correctly the OPE between Zj and Zl, right? So you pick two guys here. Let's call them Z and zeta. So Z will be one of them and zeta will be one of them. And let's look at the terms that have a pole in Z minus zeta. So how do the terms arise that have a pole in Z minus zeta? Well, there's one way in which you can get a double pole. And there's one and only one way in which you can get a double pole. You see, each of these terms has potentially a simple pole, except if you take a cycle of length 2. If you take a cycle of length 2, then you get Z1 minus Z2 times Z2 minus Z1. So you get a double pole from the 2-cycle contribution. So the 2-cycle that contains just, let's call the corresponding one P and Q. So this has AP, or let's call it A and B, right? So to distinguish it from the other AIs. So this is the guy that would involve the trace KTATB divided by Z minus zeta times zeta minus Z. So this gives you the double pole. So in order to reproduce this, what we have to assume is that the trace of KTATB is just minus K times delta AB. Okay, so that tells us how we have to normalize this trace, or rather how you define K in terms of this trace. Okay, so that will reproduce the correct double pole. So what about the simple poles? Well, there are plenty of simple poles, right? There will always be a simple pole in Z minus zeta whenever Z and zeta stand next to each other in one of the cycles, right? But think about it. So we have to sum over all the cycles. So suppose suppose here is the TA at Z, and here is the TB at zeta, and here are all the other points in the cycle. So there will be one contribution where I do whatever I do down there, and then I connect this point to this point to this, and this point to this. But there will also be a contribution where I have the same points down there, do the same stuff down there. Remember, I have to sum over all permutations. There will be also the contribution where I connect this guy to this guy to this, and this guy to this, right? If I look at a specific term where I get a pole in z minus zeta, there will always be two terms. One where it appears in a longer cycle one way, and one where it appears in the longer cycle the opposite way, right? Because, I mean, it appears somewhere in one of these cycles, but there'll be another cycle where you do exactly the same stuff on the rest, but you just connect them the opposite order to the 2 points you're specifically interested in. But we know what's the contribution. The contribution will be some stuff that will not involve a pole. And then in the first case, it will be a term that will involve trace, case, some stuff, TA, TB, some stuff, and then it will involve z minus zeta. And so let's call this guy the I1, and this, let's call this J, and call this L. So it will contain a term of the form Zj minus Z, Z minus zeta, zeta minus ZL, and then all the other terms that involve the dots I haven't drawn. And the other term will be exactly the same stuff, except that inside this trace, I reverse the order of the TAs, and then I have a Zj minus zeta, then I have zeta minus Z, and then I have Z minus ZL, right? And then all the other factors coming from all the other parts of my cycle. But you see, if I'm interested in the pole in Z minus zeta, if I'm interested in the term that goes like Z minus zeta, then there's a pole, but then to the pole term, I'm allowed to replace all Z's by zetas. So the pole term will go like, Zj minus Z times Zj minus zeta and zeta minus ZL, right? And the same will be true here, because to leading order, I can choose replace Z by zeta, and then it will go like the trace times all the terms that I haven't written, times the trace of Ka with Ta, Tb, minus Tb, Ta, because you see here we have zeta minus Z, and here we have Z minus zeta, so this produces a minus sign here. But because this is a trace of my Lie algebra, this is exactly I times FABC TC, and therefore what you're going to get is 1 over Z minus zeta I FABC TC, and then you get the contribution if you had replaced the two fields by JC sitting at zeta. So therefore, this has the correct poles, and therefore that's the answer. Because you see, the answer is uniquely characterized by having all the right poles, and the answer I've written down has all the right poles, so it must be the answer. There can't be any difference. So I can write down the correlators in closed form. Is that clear? So for example, so what does this look like for a 3-point function? Just so that you get a sense of it. Well, let's do this for the 3-point function. Okay, so what is the JA of Z1, JB of Z2, JC of Z3? Okay, so I have to look at permutations of sigma 3, but they're not allowed to have a fixed point. So there are only 2 permutations, right? Okay, so S3 has 6 elements. That's the identity that has 3 fixed points. Then there are 3 order 2 permutations. Each order 2 permutation has 1 fixed point, so they are also out. So there are only 2 permutations left, namely the permutations 1, 2, 3, and the permutation 1, 3, 2. These are the only permutations of S3 that don't have any fixed points. So what I have to write for 1, 2, 3 is the trace of K, TA, TB, TC divided by Z1 minus Z2, Z2 minus Z3, Z3 minus Z1, plus the trace K, TA, TC, TB divided by Z1 minus Z3, Z3 minus Z2, and Z2 minus Z1, right? These are the only two possibilities for permutations of order 3. And now you see this term is this term up to a sign, this term is this term up to a sign, this term is this term up to a sign. So they are just the opposite. And therefore, what this is just 1 over Z1 minus Z2, Z2 minus Z3, Z3 minus Z1, and then you get the trace of K, TA, the commutator of TB with TC, right? Because this is just the negative of it, but that is just the thing with the opposite order. So you just get that. So that's equal to FABD, TD, but the trace of this, as we saw, is minus K delta AB. So this just gives you whatever, AIFAB C times K times Z1 minus Z2, Z2 minus Z3, and Z3 minus Z1. So that's the answer. And likewise, you can do it for the 4-point function or the 17-point function or whatever, but that's the answer. And all the answers will be of that form. And you could also have worked this out by taking the OPE. If you would have done it in the OPE fashion, you would have got the FABC term from here. If you pick the central term here, then the answer is 0, because the central term would give you a 1-point function of a current, but remember, a 1-point function of a spin-1 field is 0. So you have to pick the simple pole term. So you get a simple pole term from here, a simple pole term from here, and then you get a double pole term, and if you add them up together, you also get this answer. So this is a way of writing the correlators in closed form. So the first way of doing this by just looking at the poles always works, but for the currents, there is this neat formula written in terms of these sums over permutations. There's a similar formula for Virasoro fields. So if you're interested in the correlation functions of the stress energy tensor, you can write it in terms of sums over loops, and then you write down a similar formula, and it works by a similar token. So there are closed formulas in that case. In general, it's more complicated, but you can always work it out recursively. So this just to give you a sense what these correlation functions will look like, and that you can actually work them out very explicitly. It's not inaccessible at all. Okay, so this was more of a side issue. But so one of the things you should notice that all correlation functions will be proportional to K, because the trace is proportional to K. So therefore, if you're sitting at level 0, then all your correlation functions of all your currents are 0. And likewise, in the Virasoro case, all the correlation functions will be proportional to the central charge, because at the end of the day, you have to take the central term in the OPE to get something. Therefore, everything will be proportional to the central charge or powers of the central charge. So that's the structure of the correlation functions, and you can really write them out very explicitly and in quite closed form. Okay, is that clear? Yes?
Is this a form of the Wick theorem? Because it seems like you're constructing everything, even though with 3 fields you can have the matrix elements explicitly, and you're essentially constructing everything.
In some sense, it's a Wick field, but it's not a free theory, right?
No, yeah.
Right, so it's like a Wick theorem or a Feynman rule, a simple Feynman rule, but the remarkable fact is that I haven't assumed that K is equal to the dual Coxeter number, and I can write it in terms of free fermions. In generic, this is a central charge with some random fractional number, so it's a complicated theory interacting, but nevertheless, you can write down something that looks very much like Wick contractions, yes. But it's sort of non-abelian Wick contractions, right, because you get this, you get these traces. So it's a little bit more complicated. It's But morally, that's exactly what it is, yes. Other questions? Okay, you have a question?
In general, if we can write down the OPE, which is closed for any field, we can do this recursion.
There's probably similar formulas, but I think the only example where you can write it down in closed forms are the currents, for which I've just done it, the Virasoro algebra, for which I can also do it, and the fermions, for which it's really the free Wick theorem. So, yes. But it's, I mean, these formulas are neat and useful. I mean, it's not, okay, so you don't need them every day, but every now and then. Also, it's just useful to remember these formulas exist. So if ever in your future life you are tempted to calculate them, remember that there is a closed formula. Okay, so now, so far we have looked at all these chiral fields. So somehow we have now a very good, well, I've tried to brainwash you into believing that you have a very good understanding of sort of the chiral fields of your conformal field theory. But not all the fields of your conformal field theory are chiral fields. So now we have to learn how to get the rest of the spectrum under control. So the theory will also contain fields that are not chiral. So for example, I mean, remember for the case of the free boson, we had d phi. So for that, we had a mode expansion of the form a n z to the minus n minus 1. And then, but in general, we will have fields that have a left-moving and a right-moving momentum. I mean, if you know sort of a little bit what this theories on a circle will look like, the left-moving and the right-moving momentum will be correlated. And if the left-moving momentum is non-zero and the right-moving momentum is non-zero, then this field won't be purely left-moving or purely right-moving, it'll be both. So we have to understand how to understand states that are sort of not purely left and purely right-moving. Now the idea is that we can constrain these by virtue of the fact that they should form a representation of our vertex operator algebra. So the idea is all fields of the theory should sit in some representation of the chiral fields. So what I mean by that, the chiral fields, remember, they satisfy these identities of the form V. They satisfy this duality relation. And we want this sort of relation also to be true inside correlation functions that involve these more general fields. And that, in some sense, means that these more general fields will form a representation of the algebraic structure defined by that. So they will respect all the commutation relations we've derived. So in particular, so in the most naive case, so for the free boson theory, we would say the non-trivial representations will be labeled by they will be of the form a n minus 1 of a n minus l acting on some, say, left-moving momentum state. And the a's will satisfy the same commutation relations when acting on the momentum state as we've derived before. So they will satisfy this commutation relation an is equal to m times delta m minus n. And likewise, if you think about for the currents, we would expect to have some representations of the form acting on some ground state. Let's label them like that for a moment, where the j's satisfy the commutation relations of the affine Kac-Moody algebra. So what I'm trying to argue is that the other fields that are not purely chiral fields, they should sit in representations of the chiral fields. In particular, they should sit in representations of the algebra that I can make out of the modes of the chiral fields. So for example, for the currents, what we would be interested in are the highest weight representation of the affine Kac-Moody algebra. So they should be generated from some state that's annihilated by all the positive modes. And then they should form a representation of the zero modes. Right, so there should be some sum over some, there should be some representation matrix, A of M and M prime, and then it should sit in some representation. So this is a bit schematic, but I'll write it down more explicitly for SU2 in a second. And then the negative modes will sort of generate some Fock space, and it should sort of form a representation of this algebra of modes. So this is what we would sort of expect the other states of our theory to look like. Now, in general, that's all you can say, but there are special theories where you can say a bit more, and the special theories are characterized by the fact that there are additional non-trivial relations even among the chiral fields. So we are interested in special theories, so these are the so-called rational theories. They are characterized by the property that beyond these sorts of commutation relations, which we've seen generically, there are additional relations among the chiral fields. Now this sounds at first a bit bizarre, so in order to get a sense for how this works, let's look at the example of SU2 at level K. So what do I mean by SU2 at level K? So what this means is I'm looking at currents that sit in the algebra of SU2, and the central term has level K. So if I choose the Cartan-Weil basis for this, what this means is I have generators J3, J plus minus. They satisfy this commutation relation. And then I have J3M with J3N is K over 2 times M times delta M comma minus N. And I have J plus M with J minus N. That gives me 2 J3 M plus N plus K times M times delta M minus N. So this is I'd written it so far in terms of this is this algebra written in terms of Cartan-Weil basis. So here I would have written J1, J2, and J3. If I go to the Cartan-Weil basis, I have the Cartan generator and the two roots. Then for the finite dimensional Lie algebra, this is what you would call, I don't know, H, and this is E and F or something, right? So E is the raising operator, F is the lowering operator. So with respect to the term that doesn't involve the central term, that just is like the usual Lie algebra. So J3 with J plus pi, this is plus minus J plus minus. J3 with J3 is 0. J plus with J minus gives you 2 J3. That's the usual SU2 algebra. And then the affinization means mode numbers add. And then the central term can only live between 3 and plus and minus. And the central term, the correct normalization is off by a factor of 2. And this is K over 2, and this is K. So this is sort of the Cartan-Weil basis of the affine Kac-Moody algebra associated to SU2. Okay, so this is the algebra for SU2. And now you would have thought that the Fock space of your vacuum representation, the Fock space of the chiral fields, would just be made of all the negative modes of these guys acting on the vacuum. So we would have thought that the space of states of this theory will consist of all the fields of the form, say, J plus minus, N minus, and that's right, JA, where A is an element of plus minus N3, right? And you can use the commutation relations to sort of bring them into standard order, right? I mean, you can always make sure that the mode numbers, or the positive mode numbers kill, the zero modes kill, so you only have negative mode numbers. You can arrange the mode numbers to get more negative as you go to the left. because if they're not, you simply apply the commutation relation. In the process of applying the commutation relation, you replace 2 j's by 1 j or 0 j. So after a finite number of steps, I mean, it's a recursive procedure that terminates, that allows you to bring the j's in the form where the n's are becoming more negative as you go to the left. And if 2 n's are the same, then you can insist that the plus is to the left of the 3, is to the left of the minus, or whatever you want, right? I mean, you can bring them into some standard order. And because the commutation relations, you always lose a j when you apply it, it's a finite number of steps that allows you to bring them into standard order. So you would have thought there is a basis of the space of states that is basically of that, provided I impose some standard order on the modes. Once I've imposed some standard order on the modes, there's nothing more I can do, right? I've brought them into standard order, and I would expect all of these states to be linearly independent. Now, generically, they are linearly independent, but the interesting conformal field theories are those where there is an additional relation, where some of them are not linearly independent. Now, how can this come about? Well, the easiest way to understand this is, as always, physicists, the easiest way we like to think of this is that we want to have a scalar product, and we want to ask when is a state sort of 0 in a scalar product. So we want to define a scalar product, and the scalar product we define by saying that JAN dagger, so J3 n dagger is J3 minus n, and J plus minus n dagger is J minus plus minus n. So this is some dagger, and once we've defined that, then we can work out, so if we call this state phi, then we can work out scalar products of psi with phi, because if phi has all of these modes, then we simply apply the dagger to turn them into modes acting on the other side. The phi has lots of negative modes acting on the vacuum, then under the dagger they become positive modes. The positive modes you can move to the right, and then you just bounce them until everything has been annihilated, and you just end up with a number, the vacuum. So you recursively by this and using commutation relation, you can calculate this for any of these states. And you would say that a state is non-zero if it's non-zero in one of these inner products. So generically, all of these things will be non-zero, and there will be no miracles. But for k being a positive integer, there's always a miracle. So what happens is that if k is a positive integer, if k is in n, then the following state, then the state j plus minus 1 to the k plus 1 acting on the vacuum is a null state. i.e., if I call this state n, then it will have the property that phi on n is equal to 0 for all phi. Yeah, so that's not obvious, right? So what I claim is that somehow this innocent-looking theory, you would have thought this will give me a basis and nothing bad will ever happen. But what I'm telling you is if k is an integer, so I can form this combination, then this state will have the property that it's 0 in all scalar products, and scalar product is basically the same as two-point functions. So this state will be 0 in all amplitudes of your theory. Okay, so let's see why that is true. So what do you have to check in order to see that this is true? Well, you have to check that it vanishes with any phi. Any phi is some descendant on something. So when you apply the dagger, what you have to check is that any positive mode will kill this state. Okay, so let's check whether any positive mode will kill this state. Okay, so what we have to do is we have to ask what is j plus n on j plus minus 1 to the k plus 1 on the vacuum. And I'm always interested in n bigger than 0. So I ask, what can I say about this? Well, that's pretty trivial, right? Because j plus, so I didn't write down the j plus commutator because the j plus commutator is 0. So this guy doesn't see this guy, so you can move it through here. When it hits here, that's obviously 0. Okay, that wasn't a big surprise. Okay, but obviously this has also got to be true for J3 of j plus minus 1 to the k plus 1 on the vacuum. Okay, so what do we do there? Well, okay, so now here we have to do a little bit more work, right? So there are k plus 1 terms. So we get the following sum. We get L is equal to 0 to k, probably. Then we have j plus minus 1 to the L. Then we have the commutator of j3n with j plus minus 1. And then we have a j plus minus 1 to the k minus L, right? So you see you have k minus L here, and 1 here. So altogether you have k plus 1. And you simply written out all the different commutators as you move it through. Okay, so this guy we can work out. In fact, we know what this is. This is just plus j plus n minus 1, right? Because that's what it is. And now you see, once you've done that, j plus n minus 1, if n is positive, then n minus 1 is greater or equal than 0. So this is a 0 mode or a positive mode. And this j plus goes through all of the j pluses until it hits that point, and it also kills it, right? Because this is either 0 or positive. All of these modes kill the vacuum, and they all slide through the j plus minus 1s because plus modes with plus modes commute. So this is also 0. Okay, so these are the two obvious relations. So the interesting relation is the last one, as always. Okay, so what can we say about the last relation? So there we have to do a little bit of work. So now we have to do this for j minus n. Okay, so let's try this. Okay, let's use the remaining part of the blackboard here. And then I probably need a bit more. Okay, so what can we say for j minus n? J plus minus 1 to the k plus 1 on the vacuum. Well, this formula obviously is equally true. It's the sum from 0 to k, j plus minus 1 to the L, the commutator of j minus n with j plus minus 1, and then j plus minus 1 to the k minus L acting on the vacuum. Okay, so far so good. Now I have to work out this commutator. So what is this commutator? So this is equal to the sum from L is equal to 0 to k, j plus minus 1 to the L. So what is the commutator of j minus n with j plus minus 1? So it's minus the commutator. So this is minus the commutator of j plus minus 1 with j minus n. Okay, that wasn't deep. And then the commutator of j plus something with j minus something is 2 times j3. So I get a term that looks like minus 2 times j3 of n minus 1 plus k. Well, it's sort of minus, but the m is minus 1. So I get plus k times delta n comma 1, acting on j plus minus 1 to the k minus L. Okay? Okay, so now the first thing you observe, you see if n is 2 or bigger, then this is still a positive mode. And this positive mode, now, okay, it doesn't act on k plus 1 j pluses anymore. It only acts on k minus L j pluses. But this argument up there, it didn't matter that I applied it to k plus 1 j pluses. For any number of k pluses, j pluses, it would have worked. So this term is 0 if n is bigger or equal than 2. So n minus 1 is positive. And if n is bigger or equal than 2, then this term is also 0. So this is manifestly 0 if n is bigger or equal than 2, because the first term just reproduces the previous argument, and the second term isn't there. So the only interesting case is the case n is equal to 1. That's the only non-trivial case you have to study. And what is this? So in this case, what you're going to get is a sum over L is equal to 0 to k, j plus minus 1 to the L. And then we have minus j3 0 plus k times j plus minus 1 to the k minus L acting on the vacuum. Now that sum we can easily work out. You see now, what is J3 on this guy? Well, the commutator of J3 with J plus is +1. So J3 on this state is just K minus L, right? Because in the zero mode, J3 zero with J plus or minus -1 will just give you J plus or minus -1. So this has just eigenvalue K minus L. So this becomes the sum, it becomes the sum from L is equal to 0 to K of -2 times K minus L plus K times, you see what survives is the state J plus -1 to the K acting on the vacuum, right? Because once I've applied this, it just is equal to K minus L, and then these guys and these guys combine me to give this state, and this is a number anyway. So everybody will be proportional to this state, and the prefactor is this prefactor. So what is this prefactor? Well, I have K plus 1 times. So this is equal to K into K plus 1 from here, minus 2 times the sum from L is equal to 0 of K minus L. The sum from L equal to 0 to K minus L is the same as the sum from L equal to 0 to K of L, because whether I sum L, K minus L or L, it's just, I flip it around. What's the sum from L is equal to 0 to K of L? It's a half times K plus 1. So it's a half times K plus 1. And therefore, it's equal to 0. So this is a null state. This is a non-trivial null state which this innocent-looking conformal field theory has. There's a state that you would have thought is non-trivial because you make it out of modes that seem like generating modes, but actually you produce something that will decouple from everything and that you should set equal to 0. Because it's really 0 in all correlation functions. It really wants to be the 0 state. And it's an elementary calculation to see that it's 0. This is how it looks like for SU2 at level K. There's a corresponding generalization for G at level K. In the general case, you have to take the highest root. The -1 mode of the highest root to the power K plus 1 is always a null state. And you can prove that it requires more work, that all the null states of these affine Kac-Moody theories are this states and any descendants of it. So this generates the entire null space of this theory, and this exists whenever K is a positive integer. So that's why the positive integer Wessel-Minor-Witten, well, I shouldn't say the word Wessel-Minor-Witten model. This is why the positive level current theories are special. They have an additional relation beyond just those that give you the affine Kac-Moody algebra. Okay, is that? Okay, so you say, so what? Well, this has important consequences. So what's the important consequence of it? So now you should think back about this annoying formula I wrote down at the beginning of today's first lecture. You see, this field is 0, and therefore, in any representation, of your theory, we should have the property that the nth mode of this field on any state must be equal to 0. You see, this field, this state, so where n is this specific state, it's J plus -1 to the K plus 1 acting on the vacuum, right? It's a specific state of my chiral theory. It's a 0, and therefore all its modes should annihilate all the states of the representation I'm looking at. These are the representations that are compatible with the structure of this chiral theory. In this chiral theory, I have an additional relation, namely n is equal to 0, and that must mean that the modes of n act trivially on any representation, on any state in any representation. But I told you how to calculate this, right? So this is of the form I wrote down. It's a descendant of something, and I told you that you can write this in terms of the modes of J, right? Because, so this is, you remember, the formula with the funny round brackets. That tells you now how to write this in terms of the modes the currents itself, because this is just, I mean, you can write this as j plus minus 1 on j plus minus 1 to the k. So you can ask, for example, what is the zero mode of this, right? So this is of the form I wrote down, and if you write this out, then you find that this equals to something. Namely, it equals to so what you find is that this is equal to Vk minus 2 right, so this is in this round notation is Vk minus 1 of j plus okay, let's get this straight. So this is Vk. This is Vk of V plus minus 1 of V plus minus 1 to the k on the vacuum. So this is if you write this in this round notation, because you see this guy has conformal dimension k plus 1. H of this is k plus 1. And therefore, if you look at the zero mode, it will be the kth mode. Once you've rounded, you write this round bracket notation. And then you can write this in terms of, so if you use this formula, you can write this as a sum over this L greater or equal than 0 of j plus minus 1 minus L of V of k plus L on the guy with one fewer, j minus plus minus k, plus the sum over L greater or equal than 0 of V of k minus 1 minus L on the state with one fewer j plus times j plus L. And then you can recursively iterate this. Now, the idea is that, you see, the representations we're interested in are highest rate representations. So let's think about, so let's suppose we have, what are the possible highest rate representations? So highest rate representations means the L0 spectrum is bounded of SU2 level K. Well, they're characterized by a spin and a magnetic quantum number on which all the positive modes kill, and it, for the zero modes act as in the spin, as in spin J representation of SU2, right? I mean, so you define some states that sit in a certain irreducible representation of SU2. The representations of SU2 are labeled by spin and a magnetic quantum number, the individual states. So, I mean, what I mean by that is that J3, 0 on Jm is equal to m times Jm, and J plus minus on 0 Jm is equal to this funny square root formula that I cannot remember, Jm plus or minus 1, right? I mean, you just on the highest rate states, you have a standard action of SU2 of spin J, and then you define the positive modes to kill it, and then the negative modes generate whatever there is to generate. And now you can ask, suppose I demand this equation, and I apply this equation to one of these highest rate states. So if I apply this to one of these highest rate states, you see what you find is that, so if I evaluate V0 of n on the state Jm, then, okay, so it's maybe not obvious, but this is a positive mode, because you see this is a negative mode. For L greater or equal than 0, this is a negative mode, and the total mode number must balance, so this must be a positive mode. So this will kill. The only term that will not kill is the term the term that will not kill will be of the form V of, will be V0 of J plus minus 1 to the K on the vacuum times J plus 0 on Jm. That's what you find from it's only the term, this term with L equal to 0 is the only term that survives if you apply to a highest weight state, because if L is positive, this is a positive mode and it kills, and these are all positive modes and they will also kill. So the only term that survives is if you have a single J plus and then you have something left behind. So if you iterate it, what you find is that this is equal to J plus 0 to the power K plus 1 acting on J comma M. That's what you find when you evaluate the 0 mode of this null state on the highest weight state of an arbitrary representation. Now, what does that mean? You see, this must be equal to 0. This must be equal to 0. Because n is equal to 0, all its modes must act as 0. So in particular, the 0 mode on the highest weight state must be 0. Now, when is the 0? Well, it must be true for any state in the highest weight representation. So in particular, I can pick this to be the minus j state. So when is this 0? Well, it's 0 if your spin is not too big, right? Because, I mean, you're moving up k plus 1 times with j plus. So apparently what this tells you is your spin must be such that once you've applied k plus 1 raising operators, you've fallen off the cliff and hit the upper boundary of your representation. So what this tells you is that j must be less or equal than k over 2. Because what you have to have is that minus j plus k plus 1 must be bigger than j. Right? I mean, once you've hit this, this would have become the magnetic quantum number minus j plus k plus 1. And this must be one of the ones that's not allowed anymore. It must be bigger than j. If it was equal to j, then you would have just reached the upper state of your finite dimensional representation, and it wouldn't be 0. So what you learn is, so this just means that 2j must be less than k plus 1. J must be less or equal than k over 2. So this has this remarkable consequence. So while you thought there would be infinitely many representations you could possibly write down, because you can pick any spin of SU2, the condition that it's compatible with this null vector relation means there are only finitely many possible choices for the representations. So the possible spectrum of your theory is very highly constrained. There are only finitely many things that can appear, because there are only finitely many values of the spin of the SU2 level K highest weight representation that's compatible with the structure of your chiral algebra. And that tells you that somehow the entire spectrum is determined by the representation theory. There isn't really much freedom anymore. There are finitely many choices, but there are finitely many choices. There are not infinitely many choices. That's what characterizes these rational CFTs. The rational CFTs are such that the vertex operator algebra, the algebra of these chiral fields, has only finitely many representations. So everything can be, there's a finite set of Lego pieces you're allowed to put together, but the Lego pieces must, in this case, all be representations that are the SU2 spin representations, with the spin being less or equal than k over 2. Yes? Yes, yes. So the general argument is in the general case, what is the condition? So yeah, it depends on how. So so for general Lie algebra G, the representations are labeled by the Dynkin labels, right? So you write the representation, the most general representation you can characterize in terms of the Dynkin labels, lambda 1 up to lambda r. And then there are these Katz labels that appear. So the highest root you can write in terms of the fundamental weights, in terms of the Katz labels, and the condition that for G at level K is that the sum over the lambda J times the Katz labels AK is less or equal than K. So for SU2, for SUN, the Katz labels are all integers. SU2 has a funny normalization. So SU2 is an unusual case because of this stupid half. But in general, it's just that the number of, so for example, for SU3, so for SU3 at level 1, the possible representations are 0, 0, 1, 0, and 0, 1 for k equals to 1. For k equals to 2, it'll be 0, 0, 1, 0, 0, 1, 2, 0, 1, 1, 0, 2. For level k, it'll be k 0, k minus 1, 1, plus all the ones that are smaller. For SUN, the similar story. And that's for the SU case. In general, the CUTS labels for SO, there are some that have CUTS labels 2, the edges have CUTS label 1, the middle has CUTS label 2s. So anyway, there's some algebraic relation and that characterizes it. And it's essentially the same argument, because I told you that this, so in general, this null vector is a theta. This is a null vector, where this is the highest root. And then you get a similar constraint, and you get, and this is what drops out once you've analyzed it. So for all the current theories, if this parameter k is a positive integer, there are only finitely many representations that can appear for the very same reason that I've sketched here for SU2. So that's the magic of 2D CFT. The magic of 2D CFT, the special CFTs that you can solve essentially algebraically are those where you have these additional null relations, and then everything becomes algebraic, because then you have only finitely many choices, and then everything is very much constrained by the representation theory. There is not much freedom left. You have really discrete choices to make, and then you can fix the parameters of the theory so that it satisfies all the crossing symmetry properties and whatnot. I sense a little bit total sense of having been flattened. What can I do to lift the spirits? I mean, this is a lot of material I'm throwing at you. I mean, I'm being told to tell you stuff for an hour and 3/4, and I have to keep you entertained. So I can obviously just say every sentence twice, but if I don't do that, then I'll just going to tell you lots of stuff, and that's what I'm doing. But please ask me, slow me down if there's stuff that's too fast or out of left field or whatever. Are there any other questions?
For non-compact Lie groups, does this take any data or somewhere?
No. So that's part of, so what I currently work on, my obsession is the Wessel-Witten model based on SL2R, because that's the Wessel-Witten model that describes string theory in ADS3 with pure Navier-Schwarz sector flux. So that is a variant of that, except it's not a rational CFT. So there you have to use slightly different technology. You can't use this method because there is no null vector. So the null vector analysis won't teach you anything. This example is also bizarre. SL2 level R, SL2R level K is also bizarre in that you also need to include non-highest rate representations. So that's another generalization that you need to deal with. That has to do with the non-compact nature of ADS3. So there are certain things that get much, much more complicated, but part of our progress in solving that theory was using technology of that kind. You just can't use it blindly. You have to understand where it comes from. You have to sort of tweak it, but you can still use it to learn interesting stuff about the structure of correlation functions, but it's not as simple as SU2 level K. I mean, SU2 level K was solved in the 80s. Now we are in the 2020s, so the world has moved on. So I'm telling you the stuff, the modern formulation of stuff that's a few years old, but the technology is still a useful technology even in modern applications, but you have to develop it further. Okay, so what can I do to not totally drive you over the cliff? So let me tell you at least, let me sketch to you how this looks for the Virasoro theories, the Virasoro minimal models. So for the Virasoro minimal models, so the Virasoro theories are the theories where you just have the stress energy tensor. So these are the theory where you just have the stress energy tensor. So the algebra is Lm with Ln is equal to m minus n times Lm plus n plus c over 12 m into m squared minus 1 times delta m minus n. So up there, the special cases was k being an integer. What's the special cases for the Virasoro algebra? So the rational Virasoro models are the models that have the form where C is of the form of 1 minus 6 P minus Q squared into P times Q, where P and Q are greater or equal than 2, I think. Yeah, 2. And P and Q are co-prime. So co-prime means they have no common factor. So for example, there is the 2, 3, 2, 4. No, 2, 4 is not allowed. 2, 3, 2, 5. And then there's 3, 4, 3, 5, and so on. And so this should vaguely ring a bell. So remember from the coset construction,